All right, so I'm Jesse, and we're going to talk about Cornus, atomic commit for a cloud DBMS with storage disaggregation. This was from VLDB last year. So this paper is about distributed transactions, and it's about the end of a distributed transaction. So we have to assume that the story so far is that we've got some kind of partitioned distributed database. The user has started a transaction, and in this transaction, the user has written some data to multiple partitions, and we're going to call these partitions participants in the transaction. A transaction coordinator has been chosen. Probably it's one of the participants, but it doesn't have to be. The user told the coordinator to commit the transaction, and now the coordinator must do an atomic commit. Either all of the writes in this transaction will be reflected or none of them will. So the classic solution to this problem since the 80s is two-phase commit. Here is a diagram from the paper with a version of the protocol. And we're going to go through these step by step. So first of all, note that the coordinator and the participants, they all have both compute and storage. So those stacks of donuts there, that's local disks. That's not cloud storage. We're not there yet. So the beginning of two-phase commit, the coordinator sends a prepare message to all of the participants, and they all make a decision. In this case, they all say yes, and they durably log that decision locally, and then they reply. Once the coordinator has collected all of the yeses, then it durably logs its decision to commit the transaction. At this point, it can tell the user that the transaction is committed or will inevitably be committed. And it also tells all of the participants to commit, and eventually they all hear it and they durably log that the transaction was committed, and they actually do the writes permanently. This middle part here is called the coordinator log delay. And it occurs because the coordinator has to durably log the decision before it replies to the user and before it tells the participants to commit. So why? Why does it have to spend this time durably logging this decision? So let's imagine a version of two-phase commit where we skip the coordinator log. We just immediately reply to the user as soon as we hear all the yes votes. What would happen if the coordinator died at this point? Well, only the client knows the commit decision. The rest of the system doesn't know what decision the coordinator made. And if the system doesn't know it, can't we just recover it by checking whether all of the participants voted yes? And no, we can't, because the coordinator could have aborted on timeout, even if all the participants said yes, because the coordinator might not have heard them in time. It could have told the user, no, this transaction's been aborted, but we don't know that anymore because the coordinator is dead. So the system can't recover the coordinator's decision if the coordinator dies. And it has to wait for the coordinator to, actually, even if we waited for the coordinator at this point, that wouldn't help because the coordinator didn't log anything before it died. So we'll forget it when it reboots. So this is why the coordinator has to durably log its decision before it sends it out to the participants and the user. So that's two-phase commit. It's been this way since the 80s. What's new now? Well, now we have cloud storage. S3, Azure Table, I guess, Azure Blob, Redis. There's a bunch of things that can be used as cloud storage. I think S3 is kind of the archetype. With cloud storage, it makes it easier for distributed databases to disaggregate compute from storage. And if storage is at a completely different layer on a different set of machines from the computation, then that means that participants can read and write other participants' logs. Writes to cloud storage, generally speaking, are durable as soon as they're acknowledged. There's some replication going on in the background so that the writes can't be lost, or probably won't be lost. And many cloud storage services permit something like compare and swap, and the authors are going to use that compare and swap feature to implement write once, which will mean that participants can write to other participants' logs without a race condition using this write once feature. So we're going to use these features. Cornus's two-phase commit is optimized for cloud storage. Not every cloud storage service is going to work. There are certain API requirements, but they're pretty simple. So Cornus needs to be able to implement two APIs on top of the storage service. Number one is log. It takes a transaction ID and a message, and a participant durably appends to its own log for this transaction. And the message is a write operation. The other of the two APIs is log once. So this is race condition proof. And a participant uses this to durably append to any participant's log. And it uses compare and swap to make this once only. And I really want to emphasize this, that a participant can write to its own log or any other log, and they can all do it concurrently and it will work out okay. The message here is either vote yes or commit or abort. The way it works is that if there's no existing message for the transaction, then this API updates the transaction and returns the message that was passed in. Otherwise, if the message does already exist, then don't update anything and return the already existing message. So it's like compare and swap. You tell it what you want to write, and it will tell you what is actually written, either the new value if there wasn't one before, or the previous value if there was one. This API is possible on top of S3, I think, and definitely on Azure Blob and a few other things that they actually implemented it on. So how is two-phase commit going to be optimized to use this API? They call this Cornus. I don't know why. That's the genus name for the dogwood tree. Maybe those grow outside the university. So once again, we've got coordinator and participants, but instead of they've still got stacks of donuts, but these stacks of donuts are not local disks anymore. The donuts are cloud storage now. And that means that they are write accessible to any of the participants, not just the participants that they belong to. So Cornus is going to take advantage of this feature. It's going to skip the coordinator log phase, because now it's the participants' own logs that are the source of truth. And that's going to save some latency, but it means the recovery is different, and we'll look at that. One question I have about this paper is, isn't the coordinator stateless? It doesn't seem to log anything, so I don't understand why it has any donuts. Maybe the authors just figured that you can't have too many donuts. I don't know. So I said that if the coordinator doesn't log anything, then recovery has to be different. So the key problem is, what if the coordinator fails before sending its decision to the participants? So here's another diagram from the paper. In this case, the coordinator failed, and there's no way to know what decision it made. But that's okay, because the participants, they time out waiting to hear the decision from the coordinator, and then they all write to each other's logs, and they see if they can get a commit into all of the logs. If they do, then the transaction's committed, or if they fail to do that, then that means that it's aborted. And the participants can actually know this for sure, because they don't care what the coordinator thought. By the way, it's even okay if the coordinator told the user that the transaction is committed, or aborted for that matter, even though the participants didn't hear it, since the participants will eventually learn the same outcome as the coordinator chose. So this avoids the thing that's known as the blocking problem with two-phase commit, which occurs if the coordinator dies here.
Jesse, what if the what if everybody voted yes, but the coordinator returned abort? You said that's a possibility.
It isn't a possibility here, because that will happen if the coordinator times out waiting for votes. It might decide to abort, right? In Cornus, the coordinator never times out. That's another difference. It always waits to hear the votes. And it keeps trying to, I guess it keeps sending prepare messages after a timeout until it actually gets an answer.
But if one participant is unavailable, the coordinator will be stuck, or?
I think that's right.
I have a similar question. If Murat is done speaking.
Okay.
So 2PC requires a majority, right? And the leader is a part of the majority. So for example, the leader fails, and we have these participants writing into each other's logs. How can they do that? Because the participants themselves, without the leader, do not form the majority. So the participants could have voted yes, but the coordinator, could have voted a no, could have aborted. So
first of all, I think that two-phase commit requires all the participants, not a majority. They're checking if there's like a write conflict or something. So if any of them votes no, then the transaction is aborted.
Got it. Okay.
And then I think the second part of your question is the same. The coordinator cannot decide to abort the transaction. One of the participants has to make that decision. The coordinator just finds out.
I see. Got it.
Well, in this model, the coordinator can write log abort to one of the participants' log if it's not reachable, and then decide abort and send to the user.
Oh yeah, that's right. The coordinate in Cornus, the coordinator doesn't actually do that. One of the participants has to do that. Right. So the answer to the second part of that question is, since all of the logs are in some sort of object storage like S3 or something, participants can write to each other's logs. And we're assuming that those logs are always available. This whole thing is based on the assumption that the cloud storage never goes down, and it's always available to all of the nodes.
Yeah, how does this compare with Paxos commit? We should discuss at the end, like the Paxos commit paper that Lamport and Gray wrote. Interesting.
Yeah, let's talk about that at the end, because I haven't read that paper, but I'd be curious to hear.
So now all the participants knows about all the participants, right?
That's right.
And if one participant is not responding, all the participants will wait for it. They will not even abort themselves.
I think that if a participant is not responding, the other participants can make it abort by writing to its log.
But I mean, the log is not responding. Like when you say log once, it takes time and it's timing out. The log once itself is timing out. So everyone will like just freeze.
No, this is confusing. So you see the blue arrows,
Yes.
how they go from the black lines to the red lines?
Black line to the red lines. Yes.
So the black lines are the nodes with compute, but the red lines are storage.
Yeah. I mean, if storage is not responding of one participant, everyone
I think that
freezes.
Right. I think that if storage is not responding, you're toast. And I don't think the paper addresses that at all. The paper deals with the possibility that a compute node would be unavailable, but it assumes that the storage is always available for everybody. So if I want you to abort and you're not responding, then I can write to your log. And then when you reboot, you'll read your log and you'll see that you've been aborted.
Yes.
Cool. So this all makes cloud storage seem kind of magical, right? Like you just store it in the cloud, it's magically persistent, but cloud storage isn't actually magic. If we didn't store everything in cloud, in some storage service, then we need to guarantee durability at the database layer. So you would need some sort of replication for the sake of durability and availability. Cloud storage is just the same thing. Writes to cloud storage are also replicated, but they're replicated at a different layer. When you write something to S3, S3 replicates it and then it responds to you okay. Since those writes are replicated, that means that they're higher latency than just writing to the local disk on a database node. In Azure Blob, the authors say that they get 10 milliseconds, which is much slower than writing to a local disk. And that's just in one data center, which is fairly low redundancy. Depending on the circumstances, you might want at least to replicate across 2 data centers, but then you'd probably be looking at, I don't know, 50 or 100 milliseconds of latency. So it's important to just keep in mind that we're not doing anything magical, we're just moving the replication to a different layer. So their evaluation of the paper, they have a bunch of charts. They implement this on a few different Microsoft services, and they have different charts for them. I'm looking at Azure Blob here because I think it's the most similar to S3, and that's what I'm most familiar with. I think they were collaborating with Microsoft, which is why they chose Microsoft services. It would be neat to see this actually implemented on S3 since it's so popular. The big deal here is that normal, Cornus only requires 1 replicated write per commit, and normal 2-phase commit requires 2. And since replicated writes dominate the latency, doing only 1 of them means that the latency is about half. So that's fairly convincing. Over on the left, you can see how both the mean and kind of the variance of latency are affected by adding more participants to the transaction. And it looks like Cornus and 2-phase commit are pretty similar here, except that just Cornus is faster, especially with small numbers of nodes. I'm curious why the P99 latency is actually lower for 8 nodes than for 6. It's a mystery, maybe it's haunted. So the sum of their evaluation is that it skips 1 replicated write per commit, and also that it avoids this blocking problem if the coordinator dies, because the participants' logs are the source of truth, and we're assuming that the participants' logs are always available, even if some participants are dead. And all of this seems plausible to me. My evaluation is that if you are using cloud storage anyway, then this would be an improvement to 2-phase commit on top of cloud storage. One of my questions here is about, what about reading your own writes? And this applies to Cornus or to two-phase commit, but I think it kind of affects this discussion. So here's Cornus again. It replies to the user as soon as it collects all the yes votes, because now it knows that the transaction will commit, but it hasn't yet. So what if the user gets this reply and then they immediately read from participant one before participant one actually commits? Then the user won't read their writes. This will violate strict serializability. So I think it would be more common, and I think this is true of MongoDB, that the user actually gets the reply here because consistent reads on all the participants are now possible. So if the user, so saving the coordinator log delay is still useful even if you're waiting for consistency, because it still comes sooner than if you'd done the extra write. But as a proportion of the overall latency, it's more like a third or less of it rather than a half of it. On the other hand, if you're doing a very write-heavy workload and you never want to read your writes, then saving, then you might save half the latency. I also think that this log delay optimization doesn't necessarily depend on cloud storage. As long as you believe that your coordinator, that your participants will stay available through some sort of replication, it doesn't matter if that replication is in the cloud storage layer or some other layer. If you believe that you can keep your participants up, then the coordinator doesn't need to log its decision. You can always recover it. So that's why I'm thinking that this might be an interesting thing for MongoDB, even in deployments that don't use cloud storage. And then my final piece of advice about this paper is that there can be disasters even in the cloud. The replication level that they chose here is pretty low, just one data center. You might want to choose a higher replication level at the cost of higher latency if you deployed something like this yourself. And that is that. Thank you very much.